Okay. So homework due Friday, got a quiz that's put up, and proposals due Wednesday night. Okay. So one thing I want to cover, and this is useful for your homework, okay? So we'll call it a homework hint. Who here started the homework? You can lie, it's all right. Okay, all right. So if you haven't started, I'd recommend starting. Okay, these, you don't want to let them get to the last minute. Okay. Now, when it comes to the homework, there's a particular problem where I'm giving you some points on a plot. Okay. And you're going to want to do a least squares fit. Now, there are lots of ways to do least squares fits, but we're going to do it as a quadratic program. Okay. And you might recall that for a quadratic program, the form is x star is equal to argmin x 1/2. Oh, sorry, I'm screwing this up. Apologies. Okay. 1/2 xt q x plus ct x. Okay. Subject to constraints. Ax less than or equal to b. Aeq x is equal to beq. All right. Now, not every quadratic program needs constraints. It's one thing you need to remember. But if you are assembling your cost function here as q and c, q as a name normally starts with h. What is it? Hessian. Oh, there's a question here. Catherine Waters, has been any luck in fixing the audio on the recording of last Thursday? Yes, there has. This is why I have backups. Okay, so as of right now, if you go click the link, it'll say the video is uploading from last lecture. So you can go watch it. I had an alternate recording for which I stole the audio from and then edited it into the video from last time. So that should be ready, if not now, in a couple of hours when YouTube's done processing it. Okay, so that should be up in high quality. Great question. You got it, Catherine. Okay. Q is the Hessian. Okay, so it's like partial squared f partial x squared. Okay. And C, that's your gradient, specifically partial f partial x evaluated at x equals 0. What that does is that x of 0 eliminates all those quadratic terms, right? Leaving just the linear terms. So you could think of these as the quadratic terms, hence the Q. And then the C as the linear terms. Unfortunately, linear does not start with C. Okay. All right. What happens to the constant terms? They don't matter, they go away. Nothing you do by the design variable is going to change that constant you've added. Yeah. So that's going to show up in this cost function. Okay. So you say, oh, well, Dr. Vicky, I'm a Hessian expert now. I can take partial derivatives. Therefore, I can take just a bunch of partial derivatives and put them into a matrix. That's what the Hessian is. Is the Hessian always square? You're right. Yes. Look at your nod. You can nod with confidence. Yes. It's always square. Okay. It's always square. So you might have your objective function, f of x, by objective function, I mean cost function. They're basically the same. Okay. It's equal to a bunch of stuff, right? And you say, okay, well, that's easy. I can take a partial derivative. This would be super cool, super easy. All right. However, for this problem here, with the with your plot, the cost function was the sum from k equals 1 to n of yk minus the quantity mxk plus b, where your decision vector is m and b. That's your line. You want to find that line of best fit. What's your m and b? Y equals mx plus b, right? So that k iterates with the number of points n, right? And how many points are there on your homework problem? 50. That's right, James. So if you were to write this all out, you'd have a lot. You don't want to take that derivative by hand, okay? There are two approaches you can take. One is, we'll call it brute force, which is you create that giant cost function, and then you use a symbolic toolbox to take the derivatives for you. Yours, put your thumbs up. I hope that's irony. All right. MATLAB has these symbolic toolbox. It's pretty awesome. Okay, for which you can take derivatives. I look forward to showing you that in more detail next lecture. Okay. But there's a better way. Okay. I think it's a better way, more computationally efficient way. Okay. Imagine you could calculate the Hessian just for that term. Okay. Or a partial derivative of that term, right? Okay. So basically, you wanted the partial derivative with respect to, whatever variable you're dealing with. Okay. What you want to do is take the partial derivative of your sum. And here's some function of MB. You can call it FK. K equals 1 to n. Okay. All right. So I'm adding up all of these things. Okay. I'll call this partial x. Now, these are a bunch of terms that are just added to each other. This is the same as saying, I want the sum of partial x of f of k, m, and b. So this means that I could take the derivative of my entire summed function, or I could not do that. Instead, I can take the derivative of all the little ones inside. Okay. And then add them all together. Okay. So you can do that for a single partial derivative. Yes. Is that cost function missing an exponent? Yes, you're right. Doesn't change my point, Aaron, but you're right. That's the squares part of least squares fit. Otherwise, it's a least fit. But I don't think it's a thing. Thank you. Thank you, James. All right. So you can take the derivative of all the individual components. So you can take the derivative of just this part here. You can't see what I'm circling. Okay. And then do that for each of your xk and yk and add them up. So what that means is you can get lots of little sub-Hessians and little sub-gradients and add them up in a loop once per point. And that'll give you your big Hessian and gradient. Okay, there's your hint. Any questions about that? Yes.
Another question about this, but I found a fix for the audio.
Yeah.
If you go to Zoom,
Okay.
and this, then you go to more. Yeah, the little dots at the top.
Mhm.
And then I guess there's a disconnect audio option.
Yeah.
Hopefully that fixed it.
I think it probably did. All right. Nice quality of life change. Thank you. Yeah,
I can tell it's hurting you.
that's fine. You can see the wincing in my voice. Okay. All right. So that's a nice hint. And it's also useful in the future that there are going to be times where you're going to have these functions. Okay. And you're going to want to take a derivative of it. And you might be tempted to throw it all at a big symbolic solver or take it on the derivative by hand. But sometimes you can just take the derivatives of parts and sort of repeat the form. Okay. Because one thing you'll notice is that if you take so because this is just a sum of the same form here over and over again, you can basically combine the form that comes out of this derivative. You're going to notice it's going to have linear, quadratic, and constant terms. Okay. All right. I won't belabor that anymore. I'll let you go from there. Okay. So keep that in mind. So back to trajectory optimization, which will be the subject of your next homework. Okay. Now, for those who were able to see the lecture last Thursday, if not, you will be able to see it in mere hours from now or hear it. What technique did we use for formulating the optimization problem on Thursday? Multiple shooting, right? So we had covered single shooting and multiple shooting. So there are methods for formulating a trajectory optimization. We talked about single shooting. And one of the issues is it's sensitive, particularly sensitive to initial guesses. All nonlinear programs are, okay, but single shooting tends to be a lot, all right? And that's because its constraints tend to be more nonlinear because you're going to be shooting over a longer shot. It integrates up lots of things going on. So your constraints become effectively more nonlinear. But if you shrink the size of your shot, it becomes more locally linear, which gives us our technique we did last time called multiple shooting. Okay. It can be less sensitive to initial guesses. However, we still have to be able to compute for the solver the gradient of the cost function and the derivatives of the constraints. Now, the derivative of the constraint is what kind of derivative? Is it starts with a J. You take the Jacobian, right? It's the derivative of a function with respect to a function, so it's Jacobian, all right? So you still need to simulate many shots to approximate gradients / Jacobians via a technique we call finite differencing. Okay. There are ways to make that better. Okay. For instance, when we coded up our multiple shooting problem, we had a constraint function that just looped through the shots. okay? And it looped through all the shots every time it wanted to, whatever was called. So that way, when solver is trying to approximate the constraint Jacobian, every time it wants to do a finite differencing step, it'll shoot all the shots, okay? However, knowing for this shot, okay, this one at the beginning, how that constraint works is completely irrelevant from this shot over here. So you don't have to simulate that shot if you're testing that constraint, okay? So you could make a smarter function, smarter constraint function that detects which design variables it's being fed and say, okay, which of these simulations, of these shots do I actually have to simulate, okay? I know you can do this because I did this as part of my PhD and it sped up my code a lot. So you can speed it up more than you're seeing. So you can speed it up more than you saw. However, there's an approach that I started to fall in love with as a PhD student, which is called direct collocation. All right. Notice the word shooting is gone. There's no more shooting in terms of your integration. You're no longer using time marching integration. So does not use shooting or time marching integration. Okay. It approximates the state trajectory using functions, say often splines. We're familiar with splines already, right? That's how we represented our control inputs. Okay. So it approximates the state trajectory, right? So we're not actually simulating anymore. Okay. And instead, let's see, it enforces the dynamics as constraints along the state trajectory. I want to get that up front as to what direct collocation is doing. And now I'll talk about it in more flourishy language, okay? In multiple shooting and single shooting, all right, in both of those situations, you have your optimization that's sending in decision variables to your simulator, and the simulator sends back what all the states are, right? One hands it to the other and back, okay? Direct collocation, we take the simulator and we throw it away. Now the optimization itself is doing the simulating. It does that by encoding the dynamics as constraints. It's kind of wild, okay? And I will draw for direct collocation what I mean. So let's draw our example control input, U of t, on a plot. And we had these nice connecting points. I draw them as piecewise linear, but they do not need to be piecewise linear necessarily. They want to draw my single system state, x of t. And instead of doing shots, I'm going to represent my state trajectory as a spline. some random points here. Try to draw them slightly more randomly. It's a little aside, but you know that people are very bad at generating random numbers. We tend to not pick the same number twice. It's a pattern among human behavior, and it's a very good way to find out if people are faking data. People can do analysis to show that if they don't repeat the same number multiple times, that it's probably faked. People have done this to show fraudulent political polling in the past. Pretty cool. Anyway, what's connected with some splines, some curves? Okay. Connected with a spline. It can be linear, it can be higher order, your choice. So now we're going to connect and there should be one per the same number of nodes. I just drew it a little sloppy. We're going to connect our points with splines. I'm going to circle all of our decision variables. So looking at what I just circled, what does direct collocation have in common with multiple shooting? Anybody?
Decision variables.
Yes, the decision variables. What about the decision variables in particular?
That they're in the same location.
Yeah, pretty much in the same location, but specifically that while single shooting and multiple shooting all have decision variables for our inputs, okay, single shooting doesn't have decision variables for our states along the trajectory. Multiple shooting does, because that's how we determine how each shot takes its shot from the initial condition. Okay, as does direct collocation. Direct collocation also has decision variables along the trajectory. So both multiple shooting and direct collocation have decision variables along the state trajectory, unlike single shooting. Okay. Now, I'm going to take a different color. I'm going to go to my state trajectory. And I'm going to find a point in the middle of the trajectory, in the middle in time. Okay. Okay, and these points, they're called collocation points. Okay. And we're going to go to each of those collocation points and draw a tangent line. All of them. This is beautiful. I love how direct collocation works. Okay, so the slope, what we're going to look at is the slope of these tangents. Okay. Now the slope of these tangents is rise over run. Our rise is our change in what? T? X? X. Yes, that's the rise, right? So slope is equal to delta X over run. What's run? Time. Delta T, right? Okay. Now, delta X over delta T. Let me move that. Look at that. I can use an iPad now. How about that? I've made it. Delta X over delta T is approximately dx dt, which is equal to x dot. Now, if I say that x dot is time varying, for instance, do we have some key relation? Anyone remember our first ordered form? Yeah. X dot is equal to f x of t u of t. That's our first order form. So we enforce our dynamics as constraints on slope. And this is super cool because in multiple shooting, we had constraints along the trajectory, right? Anyone remember those? We had a name for them, started with a D. Defect constraints, right? And what were those defect constraints? Can anyone describe to me in words what those were?
The difference between the end of a state and the beginning of another state.
Yeah. So you're exactly right, Egwu. It's the difference between the end of a previous shot, where it ended, and their next decision variable, right? Whether those lined up. That defect told you whether or not you're going to have sudden jumps in your state space, which are impossible for a continuous system. Okay. So you had defect constraints along your trajectory. Now, this is your defect constraint. The difference between that slope and your dynamics. So delta x, delta t, or your slope, needs to be equal to f of x of t u of t. That's a defect constraint. And you want to apply that to every one of those collocation points. What a weird, convoluted way to simulate a system. Why the heck will we do this? Well, what was one of the reasons that multiple shooting has issues? When it's trying to get its derivatives of its constraints, it needs to keep resimulating the system, right? And then do finite differencing. Well, here though, let's look at an example. Let's say we have a differential equation for x dot of t. Let's just create a differential equation. Say it's minus g over L sine of x of t plus u of t. This is an example. Well, guess what? I can take the derivative of that with respect to my decision variables algebraically. Say, with mechanical systems, and many other systems, f of x of t, u of t, is a symbolic function. And thus, we can take a derivative analytically. So excited, I'm screwing up. So excited. So that means when you set up your optimization problem, you can actually have not only a function for all your constraints that is just a bunch of algebra. You can also create the derivatives of all your constraints that's just a bunch of algebra. And that's really fast to solve compared to running many simulations. And so, see, this makes gradients and Jacobians much faster to compute. Is something. But also smoother. Okay. Because if you're using finite differencing to compute a gradient or a derivative, you're picking 2 points, you're computing a slope. That's an approximation, and that can add actual noise to your derivative signal. That's not good. That can confuse the optimizer at some points. Here it's an exact derivative. No approximation at all of the derivative when you're of the derivative, that is. Okay. Okay. So that means that every iteration of the optimization, your solver is going to take your cost function and it's going to put in a value. What's my cost? Boom. Guess what? That's just going to be a function, like a math, like a math function of symbolic stuff. Super fast, right? It's gonna ask, what are my constraint values? Well, it's gonna take in your constraint equations. Well, guess what? They are all just a bunch of algebra, right? Plug in values, boom, out comes all the constraint values. It's gonna say, oh, what's my gradient of my cost function? And it's just gonna put in values into your new gradient of your cost function, which is just a bunch of math algebra. Goes through, boom, very fast. And your constraint Jacobian, same story. Okay. Now, sounds wonderful. What is from what I've described to you so far, what is a downside of direct collocation based on what I've described? And I'll give you a hint. It goes all the way back to here.
Linearize your dynamics?
No, you don't have to linearize your dynamics. They're not linearized, but you are approximating your dynamics as a spline. Okay. That is not strictly speaking true. Your dynamics do not necessarily follow the curve that you described in shape, right? You could have linear splines. You can do that. Your approximation will be worse, but and it would be worse. Okay. But you can still solve a direct collocation problem like that. So the issue, so downside, direct collocation uses an approximation of the dynamics via its splines. So if your accuracy is super important, you want to be careful with how you use direct collocation. Now, in practice, though, if you're doing optimal control, you are rarely relying only on open loop control, where you are doing a trajectory optimization. You say, okay, fantastic. I've done my trajectory optimization. I know what torques I want to apply to my system. It's going to go there, right? Well, in real life, things aren't perfect. Things bump into your system. Your equations are probably wrong anyway. Well, guess what? They are wrong anyway. All models are wrong, but some are useful, as many people have said. So in practice, Trajectory optimization is often used for generating feed forward or open loop control. So might have some U of T into the system. Comes out as some output. Okay. All right, but in reality, we often use feedback control to stabilize your trajectory. So you might have some input, which will be like a reference, R of T. It's a reference. Reference. That will go into a summing junction, goes into some feedback controller. Goes into our system. And there's some feedback. So comes out as some output, Y of T. We subtract R, we subtract it from R of T, that gives us something called an error. That error goes into a controller, which comes out as U of T into a system, right? And that reference can be generated by trajectory optimization. And because there's already a stabilizing controller that's that's correcting for little errors, those little differences in the dynamical approximations might not matter. Okay. So yeah, so it is a weakness that direct collocation approximates the dynamics, but it's not the end of the world. Okay. So let's actually write out a direct collocation formulation. Okay. Let's do an example. Of direct collocation. One of my favorites is not the pendulum. Call it the double integrator. It's the moving a block. Sliding on the ground. This might look familiar if you're doing if you're on top of your homework, by the way. Okay. Where it's going to apply a force to this block. It's going to have some distance it's going to move, S of T. There's going to be some final distance we want to get to. And we'll start at 0. Oh, no, back. Okay. Okay. All right. And we want to, let's do a minimum time. Optimal control problem. subject to the constraint that we have some limits on f of t. It's gonna be greater than or equal to minus f max and less than or equal to f max. Now, the solution to this problem is pretty intuitive. Probably talked about it before many times, that basically you stomp on the gas, then you stomp on the brake at the right times. It's the right answer. We know it's the right answer. Okay, but how do we get an optimizer to give us that answer? Okay, so let's formulate this as direct collocation using linear state splines and constant input splines. Okay. I'm defining the splines I'm going to use beforehand to make it clear what we're going to do. So I'll draw this out. And so I'm going to say, here is our u of t. It's going to be an input over time that ends at some t, capital T, which we're going to have to define as a decision variable because we want to find the minimum time, right? I'm going to create some points. I'm going to draw 6 points just on my screen for clarity. And they're going to be piecewise constant inputs. Okay. Okay. Now, for my states, well, first we got to know how many states I have, which means I need to know what my dynamics are. They're not too complicated. Say S double dot of t is equal to f of t over m. And sliding without friction, we won't have a friction term in here. Call a double integrator because, hey, there's two integrals on s, two derivatives on xs, so we have to integrate it twice. Okay, very clever. Okay, we're going to have two states. We're going to say our state vector is s and s dot. We say it needs to be integrated twice because we have constraints on s. We want it to end at a particular point, right? So we have to integrate it twice, so we need two states. So we're going to have our first state, we'll call it S of t. Ends at t. We have 6 points along our input trajectory. We'll also have 6 points along our state trajectory. Okay, and these will be piecewise linear. 2, 3, 4, 5, 6. And similarly, we have a second state. So we need decision variables for that. So S dot of t. Some final time. There's going to be 6 points. Again, I'm just drawing them arbitrarily. 3, 4, 5, and 6. We're going to connect these with piecewise linear splines. Okay. I'm going to circle all my decision variables. In good old blue. Okay. So I'm circling all of my control inputs and all my states. See that? Also, don't want to forget, we're going to do a minimum time problem. So we're also going to need to know our final time. Yes.
Last lecture, you called the first state the initial condition.
Yeah.
Is it different?
You could do it. Great question, Jonathan. Okay. You could do it either way. Okay. So I've created a decision variable here just for generality. Okay. What would I have to do to make that my initial condition in my optimization problem? If I have a decision variable for my initial state, make a constraint, right? If you know that initial condition will never change in your problem, right? You can just say, you know what? That's my initial condition. It's going to be a constant, not a decision variable. Okay. Or you could just make a constraint. I'll also say that another potentially superfluous variable, I'm going to draw an arrow to it and I'll just delete it. Look at that. It'll never experience that force. Boy, look at me, a beautiful arrow. How about that? Technology. Okay. Right. So there are things you can get rid of if you want to. So be aware of that. I'm drawing this out in generality so you can get rid of completely superfluous decision variables if you need to. Okay. But here, so now we're going to have our decision vector X. It's going to have U1 through UN, S1 through SN. Get this a little bigger. And then S dot 1 through S dot N. And finally, T. You put this in whatever order you want, to be clear. Right? Okay. U1 through UN. So those are all your decision variables. So that's your decision vector. Okay. Now our cost function, if we're saying, hey, X star is equal to argmin of f of X, subject to the constraints that you have some G1 of X is less than or equal to 0 and some G of X, G of 2 of X is equal to 0. So argmin f of X. F of X is a function of our decision vector. What is it? Anybody? What are we minimizing? T. Capital T. Minimizing time. Super easy, right? Now our inequality constraints, we have inequality constraints. G1 of X is less than or equal to 0. Do we have any inequality constraints in our problem?
Yes.
What are they?
T is greater than negative X.
Yeah, it's the force limits, is what you're saying. Perfect. Exactly right. This is going to be our force limits. We're going to say U1 through UN is less than or equal to some F max. And also we're going to say that they have to be greater than or equal to minus F max. So another way of saying that is that U1 through UN minus U1 through minus UN is less than or equal to F max, using the tricks from your first homework, right? You flip around the sign using negative signs. Now, the tricky part are the equality constraints. G2 of X is equal to 0. Here's your equality constraints. So as Jonathan Boylan pointed out, we have to have some constraint on our initial conditions, right? So we want to say that S1 is equal to 0. S1 dot is equal to 0. This is its initial condition. Or Boylanian initial condition. Right? We have our final condition. We want Sn to be at whatever our final position is. We'll call it SF. We want it to be at rest. So that's our final condition. But then the meat, the heart of it all, are going to be our defect constraints. So we need our defect constraints, which are our slope equals our dynamics. So to do that, we want to make sure we have our dynamics, which are in first order form, that x dot is equal to f of xu. So we would write that out that, oh, q dot is equal to the derivative of our first state, and then a derivative of our second state, which is equal to our second state s dot, and f of t over m for our acceleration. That's our, put it as q dot is equal to, goodness, h of q u. It's our first order form, just without using the letter x. Our first order form. That's our dynamics. Yes, question.
Kevin's got a question.
Oh, question. Do we need to add a constraint for time to be positive? Oh, you're so smart. Kevin, best. As many have probably said, you're very good. Because we did that for multiple shooting, right? Kevin, excellent. Correct. T is greater than or equal to 0. Therefore, minus t is less than or equal to 0, right? Okay. So that's the dynamics part. What about the slope part? Can we have an equation for our slope of our system? The answer is yes. Okay. It's rise over run, right? So there's going to be a change in the vertical position. So for S, it's going to be S I plus 1 minus S I over run, which is change in time, right? So our change in time is going to be not our full time. It's going to be a subdivision of that. So it's going to be t divided by our number of nodes minus 1. Why the minus 1? It has to do with barriers between farms. It's a word for it. The fence post problem, exactly, Egwu. You have n fence posts, that means you have n minus 1 windows between them. Okay. I know my iCloud storage is full and I do not care. Okay. So that's your slope, right? That's for our states S. And then, of course, it's for our states S dot, it's no different. S I plus 1 minus S I dot over T divided by n minus 1 for our states S dot. Nifty. So those need to be equal to our dynamics. So let's write an example of this for our states S. Okay. And that means that Si plus 1 minus Si over T n minus 1 is equal to, what are our dynamics of, what's the derivative of S? It's S dot. Okay. And we'll actually say S dot I. The fact that we chose S dot I and not S dot I plus 1 is a choice that we made. Okay. It actually reflects the type of integration that we are implicitly doing. We are taking the derivative of the previous state. We're going to be multiplying it by some delta t, right? And adding it to the previous, and adding it to our previous s. Does that sound like any particular kind of integration? What's that? It's a very simple Runge cut. Technically, you're right. Everyone remember Euler's method? It's Euler's method. You'll see it in just a second. Okay. So that one, I'm going to solve this out to give us Si plus 1 is equal to Si plus Si dot times T over n minus 1. It's the worst squiggle I've done. And that's almost better. That's just delta T. It's what we call explicit Euler. So that choice of spline, where it's a piecewise linear, okay, and we use the state from the beginning, not the state at the end, I plus 1, we effectively made an explicit, or sometimes we call it a forward Euler, approximation of the integral. If you were to choose Si plus 1 dot, it would be an implicit or backward Euler integration method. You could choose the average of your two states, at which point it's no longer a piecewise line. It would come out as a quadratic approximation. The average of your two states, it's a trapezoidal method. So that's with a quadratic curve. You could do a cubic curve. That gets a little bit more complicated because there are more degrees of freedom to a cubic curve. You would actually have to add another decision variable in the middle to define that cubic curve, fully define it. And that's a method called Hermite-Simpson. Okay. Could you do a quartic curve? Sure. I don't think I've seen it done. People often stop at cubics. Okay. And what might you get if you increase this order of the polynomial? What's an advantage of that? Yes.
You get more accurate results.
You get more accurate results, exactly. Get more accurate results. Okay, we'll cover all that more next time. Okay, when we're coding this up. But that's a defect constraint. And you do it for all I, sorry, for all I is equal to 1 through n minus 1. You don't want to do it through n because you'll end up adding an extra 1 to it, which makes sense. It's a fence post problem. You have n points and you want to connect it via n minus 1 defect constraints. All right. Now, similarly, for our SI dot plus 1, we can use the same explicit Euler form. This would be SI dot plus SI double dot, but we know what that is. That is F over M. Which F do we use? We're going to use F I over M times T over n minus 1. That is SI double dot. Again, using the forward Euler, explicit Euler approximation, using the previous state and multiplying by delta T, right? Okay. And again, you do that for all I is equal to 1 through n minus 1, right? And that's it, unless Kevin Awesome remembers another constraint I've missed. Okay. I'm good, thank you, thank you. Great. Cool, so that's all our constraints. Now, using the powers that you have been developing for putting constraints into MATLAB, you can just put this into MATLAB and it'll solve, right? It will. Now, that's cool, right? One thing that's enough to put it in a solver. However, that solver, it's coming up with its own derivatives, right? It's using finite differencing to find those derivatives. Okay. Oh, I'm blurry. Camera guy. Okay, good. All right. So in FMinCon and many solvers, there's an option where you can give it the derivatives for it. And that will tell it, oh, I don't have to compute the derivatives via finite differencing. Right? So further, you can provide most nonlinear programming solvers with your own derivatives too. You could give it partial f of x, partial x. That's your cost gradient. You could give it partial g1 of x, partial x, and partial g2 of x, partial x, as constraint Jacobians. We have 5 minutes. We can do some constraint Jacobians, right? Okay, I see some tepid faces. Okay, but I'll convince you. In reading through the camera, tepidity, I see it. But we'll do it. Okay. Let's do an example where we will just deal with our equality constraints and just the defect constraints, okay? We'll just do the defect constraints. So we're going to do a partial derivative of g2 of x, partial x. We'll do just the defect constraints. So let's start with our first defect constraint, which was SI plus 1 is equal to SI plus SI dot times delta T, where delta T is equal to T over N minus 1. You could put that all on the left-hand side, and you could say SI plus 1 minus SI minus SI dot times delta T is equal to 0. I'm going to take a derivative. So that right there, call it G. Let's call it G for the moment. Say partial G. I'm going to take a partial of just some of our decision variables to keep our Jacobian reasonable, okay? Because we have a lot of decision variables, right? If n equals 10, we have 31 decision variables. So what's the size of my, how many, so that's 31 columns to my constraint Jacobian, no thanks. For now. And as many rows as we have constraints, which is 27 plus 3, including the Kevin-Destian constraint. Okay. Happens to be square in that case. That's not generally the case. Okay. SI dot, and take respect to SI plus 1, SI1, SI dot plus 1. So we have a single constraint here. So that would be, for this Jacobian, a single row with 4 entries. So partial S, partial SI is just a -1. Partial G, partial SI plus 1. There's just a +1. Minus, then you have a minus SI times delta T. Okay. So that's going to be minus delta T, which is T over Ni minus 1. Oh, and at the end, I have to include T somewhere, right? Right. Partial SI dot plus 1, there is none. SI plus 1 dot. Okay. And minus SI dot over N minus 1. Oh no, I'm out of space, excuse me. Okay. All right. So for that part of the Jacobian, I computed that row, right? And I is going to increase along my, is going to increase for all of my different constraints, right? So I can look at my overall partial G, partial X, which is going to be some big old matrix. And somewhere in that matrix, there's going to be, oh, a -1, 1, a minus, somewhere a minus T over N minus 1, 0, and N. And at the end, some minus SI dot over N minus 1. And because I is incrementing, the row, I'm going to draw this here, the row is going to increment along with it with each new constraint, which means that the entries in our Jacobian are going to move like this. Kind of like that. You're going to move along a diagonal. And the same thing for minus T, N minus 1, 0, minus T over N minus 1, 0. Going to move along diagonals. Okay. where everything else are zeros. See, note this Jacobian is sparse, and I'm going to finish up this last point. That means most entries are zeros. And that's helpful numerically for the solver. Okay, there are smart ways to manipulate matrices with a lot of zeros in them. It's also easy to build a matrix with a lot of zeros in there. You just create a big matrix of zeros. And if you know that these entries are going to have a particular form, you can use very simple MATLAB or Julia commands to systematically insert all those values in that pattern. Okay, so that's what that's what the Jacobian looks like. Okay, it'll have like this kind of cool diagonals in it, and you give that Jacobian to your F-min con or your solver, and it has a much easier time solving. Okay, but that's for next time. Thank you all so much. Thank you all so much.